Okay, after that, we have to possibly have to get the news. Today? What a problem. Yeah, what check it. For today, there is yeah. So let's go to tomorrow. What was that? What after the interview of
Okay, maybe we can get started. We're very happy to have Surya Raghavendran with us today. He's going to tell us about twisted 11D supergravity and infinite dimensional exceptional simple superly algebras. Please take it.
Great, thanks. Thanks for the opportunity to speak. It's been wonderful visiting so far. So I'd like to tell you about some work that I've been doing joint with Ingmar Saberi and Brian Williams. And most of what I'll say is based on these two papers here. And before I begin, I should maybe give a caveat. I am a mathematician, so please feel free to stop and ask questions if anything's unclear. Okay. So the main player in my talk will be 11-dimensional supergravity. So this is the unique supersymmetric theory in 11 dimensions, and it's supposed to describe the low energy limit of M theory. It was introduced in the 80s in a paper of Kremer, Julian Shirk, as I'm sure people are aware. And part of its appeal is that maybe unlike many theories of supergravity in lower dimensions, the bosonic field content is relatively simple. It just consists of a metric and a 3-form, right? And one of the many curious features of this theory that was maybe observed in the early days is that it has a close relationship with exceptional series, Lie algebras and Lie groups. So one thing that was observed is that upon considering toroidal compactifications, exceptional series Lie groups appear in its U-duality. This becomes particularly interesting starting from compactifications on T9, where the Lie group that appears is infinite dimensional. It's an affine Kac-Moody group, E9. And the pattern continues, and toroidal compactifications on T10 and T11 are supposed to yield hyperbolic Kac-Moody groups inside the U-duality. Okay. So today I'll describe another appearance of exceptional symmetries in 11-dimensional supergravity, but of a slightly different flavor. So one difference is that the objects that appeared, they'll be infinite dimensional, exceptional, simple super Lie algebras. So these were classified by Katz and Shapachnica in the late 90s, and there are 5 exceptional entries. I've labeled 3 of them here. And we'll find that these 3, they'll appear when we place 11-dimensional supergravity on various backgrounds. And the backgrounds won't be associated to tori, but rather they'll come from performing an operation like a twist. Okay? So this was yeah, so this is E5/10, this is E3/6, and this is E1/6. I will define these later on, but maybe just to get a sense of the numerology. So these are superalgebras. The even part will contain something like vector fields on C to the first number, and the odd part, the number after the slash sort of tells you the rank of the odd part over functions on C to the first number. So they're very big.
So, but you're not talking about, there are the infinite dimensional bosonic ones like E10 and so on.
No, these are different from those. Yeah. As far as I'm aware, yeah.
Special thing about this exception or infinite dimensional extension of exceptional real algebra is what I have written on right. I can't fully read it.
Yeah. So this will be the contents. Explaining this will be the contents of the talk. So there's an operation similar to a twist that you can perform to 11-dimensional supergravity, and then the twist can be placed on various backgrounds, flat space, R times C5, and then versions of the ADS7 times S4 and ADS4 times S7 backgrounds. And these super Lie algebras will appear as symmetries of the theory on those backgrounds.
Are the exceptional ones special in this sense, or even the other infinite dimensional extension of super Lie algebra stuff? I don't think it's special.
I think this is something special about M theory, or I can say, well, okay, there are other non-exceptional entries that will appear as symmetries of other twists of supergravity on flat space, say. Yeah, that's certainly
This
true.
is the analog of what Costello and Lee did with the type 2B on APS5 times S5 or on C5 or something.
It's very similar to that, yeah. I think the so the sector of type 2B that they extract will be very similar to, or the way I'll define this twist will be very similar, but I don't think they actually identify the algebra that's most analogous to these in their paper. So there's some other super Lie algebras in Katz's classification called the SHON/N, which are divergence-free Hamiltonian vector fields on Cn/n with respect to the, where Hamiltonian means with respect to the odd symplectic form on Cn/n. And for n equals 5 and n equals 3, those Lie algebras will act as symmetries of the minimal twist and the Costello-Gallardo twist of type 2B on flat space. So it is very analogous to something that goes on in that story, yeah. No, there are two others. I don't know how they're related to supergravity. Yeah, I have some speculations in that direction, but maybe ask me later, yeah. Okay. Cool. So let me begin.
These are the only, you're saying, all the infinite dimensional, exceptional, simple super Lie algebras that we classified? And
They've been classified. So other than these three, there are two more. And I'm not quite sure where those appear in the context of in physics, I guess. Yeah, it'll be, yeah, I have some speculations about that, but it'll be easier to maybe state them after I've maybe told you about what some of these algebras look like. And, yeah. Okay. So let me begin by saying some things about what I mean by twisting. My perspective might be slightly different. Gosh, this is probably very small. Okay. Let me try.
Okay, switch off the screen network. On this blackboard.
Okay, there aren't too many handwritten slides. There's just this one and one more handwritten slide, and then everything else is text. So for the time being, I'll also just like read things out. Okay. Okay, so of course, in a supersymmetric field theory, the space of fields, it carries an action of a supersymmetry algebra, may only close on shell or up to a gauge transformation. Throughout my talk, I'll treat field theories in the BV formalism, so dealing with those sorts of subtleties about off-shell formulations of supersymmetry is maybe not so bad. So what do I mean by twist? So given a square zero supercharge, I can look at the invariance of the space of fields with respect to the rank 0/1 subalgebra spanned by that supercharge. One way to model that is to add the supercharge to the BRST differential and then take cohomology with respect to this totalized thing. And the results will be a dramatically simpler theory. So the image of Clifford multiplication by the supercharged Q that determines a subbundle of the complexified tangent bundle, which is something called a transversely holomorphic foliation. So it's something that you can think is maybe somewhere in between complex structure and topology, and the twist will sort of only depend on that kind of data. So it'll be a holomorphic topological theory. And those kinds of theories are very nice for a number of reasons. There are some results that tell you that their perturbative quantizations are maybe as nice as can be, as long as there's one topological direction around their UV finite. Another feature that will appear in this talk is that they often admit infinite dimensional symmetry enhancements that you should think of as very akin to the appearance of the Virasoro algebra 2D chiral CFT. And lastly, there's pretty good language for describing the structure present on local operators together with their descendants and secondary operations. In math, these structures called EN factorization algebras. So the output of this procedure is a much simpler theory. And so I wanna emphasize for me that by twisting, I really mean this procedure where I take invariance with respect to a square zero supercharge. I'm not going to emphasize the part of the procedure where you maybe want to choose a subgroup of spin times R symmetries with respect to which this transforms as a scalar. From my perspective, if you care about a local invariant like space of local operators or something like that, this is sort of the more drastic operation, and you can sort of just look at the stabilizer of the supercharge, and that'll determine what kinds of manifolds you can globalize the twist on. Okay.
So said this that saying that this twisting operation naturally comes with the infinite dimensional symmetry enhancement. I mean, it follows directly from it. Or you're saying that
That's
to be the case in all the examples.
I'm saying the latter. There's if I start with a super conformal field theory, then I think there's something close to a proof that this will always happen. But for a general supersymmetric theory, it's sort of an experimental result. Yeah. Okay. Now there's a variance of this kind of construction that you can perform for a superconformal field theory. So this is this Q plus S type construction that appears in work of Beam-Rastelli et al. So if I have a pair of a super translation and an odd superconformal symmetry that satisfy these relations here, then I can also look at the invariance with respect to the superconformal element. And the result will be now a lower dimensional field theory that's supported at the fixed points of the infinitesimal action of B here. Okay. So this is the kind of construction that's used to extract, for instance, like chiral algebras from 40 n equals 2 theories of class S. And, okay. Great. Oh. Okay. So as a warm up, let me maybe describe some examples of the latter type of construction. So here's a theory which arises as what's called the minimal twist of the rank 1 ABJM theory at level 1. So whenever a theory has a twist, it has what's called a minimal twist, which sort of remembers a maximal amount of information of the parent physical theory as possible, or the rank of this transversely holomorphic foliation that the theory depends on will be sort of as close to half-dimensional as possible, okay? So for the rank 1 ABJM theory at level 1, the results is a holomorphic topological theory. So it's defined on things that are locally R times C. And so I said this earlier, but throughout this talk, I'll describe theories using the BV formalism. So when I write fields, for me, a linearized theory will be described by a cochain complex that includes all the ghosts and anti-fields and anti-ghosts and all that. So the minimal twist looks like the following things. So I have the Drum complex on R tensor the Dolbeault complex on C with coefficients in 4 copies of a quarter root of the canonical bundle and 4 copies of k to the 3/4 parity shifted. And I'd like the second 4 copies to sort of transform in the anti-fundamental of SL4. Okay. And since I'm on flat space, I can of course just trivialize these bundles and write the space of sections of these is an exterior algebra on 3 generators. Okay. So in this notation, I can perform one of these superconformal deformations, and it looks like deforming the differential here, which is just the Drum differential and the Dolbeault operator, by a differential that looks like Z del epsilon 3, okay? And if you look at what this differential is doing, it's resolving the equation Z equals 0 along C, okay? So if I take cohomology with respect to this, it kills off this epsilon 3, and it localizes me to 0 here, okay? So the result, it just looks like the Drum complex on R adjoined 2 odd generators, okay? So this deformation has taken me from a holomorphic topological theory in 3 dimensions to just a topological theory in 1 dimension. One thing we'll see later in this talk is that this theory has an action of an infinite dimensional Lie algebra E16, called E16. And upon doing this deformation, that Lie algebra gets broken to something finite dimensional, just the SL2 that's acting here. Okay. So another example is the minimal twist of the 62-0 abelian tensor multiplet. So this was computed independently by my collaborators. And the fields look as follows. So I have a resolution of holomorphic closed 2 forms. The differential here is just the holomorphic Drum differential. They also have 2 holomorphic sections of k to the half parity shifted. And there's a very similar deformation. It's the one that's considered by Beamer-Rosselli et al. In their paper on W symmetry in 6 dimensions. It's sort of just written in the language of this minimal twist. And the result of doing that gives you this complex here, resolving co-closed 1 forms, which describes just a free chiral boson. Okay. And again, there's an infinite dimensional Lie algebra that acts on this thing called E36. And after doing that deformation, it gets broken to the action of just vector fields on C. Now, of course, there's a richer algebra here, the Virasoro algebra, which acts on the space of local operators. where vector fields on C occurs as sort of just half of the modes. And analogously, E36 sort of appears as half of the modes of a sort of higher version of the Virasoro algebra, which will act on local operators of the minimal twist of any theory with 62, 0 superconformal symmetry, but that sort of higher Virasoro algebra won't feature in my talk today. Okay. Okay. So that's what it meant. I described what it means to twist a non-gravitational supersymmetric field theory. Let me now describe what it means to twist a theory of supergravity. So because supersymmetry is gauged, it's a little bit more subtle. So here I've written schematically the PV complex for a theory of supergravity. There's a bigrading by Gauss number and by fermion parity. So I want to draw attention to this field here, which is it's odd with respect to fermion parity, and it's of Gauss number -1. So with respect to the total degree, it's bosonic. So Costello and Lee defined a twisted supergravity background as supergravity in perturbation theory around a point where this field, the bosonic ghost, it takes a non-zero vev, which is the equations of motion is required to be nilpotent and a covariantly constant spinor. So I'm told this appears earlier in the literature. I learned it from here though. And so why is this a good definition? So there's maybe two features that make this definition worthy of being able to twist. So one is that twisting a non-gravitational supersymmetric field theory, in the sense that I previously described, it's the same as coupling to a twisted supergravity background. You look at where this bosonic ghost Q enters into the coupling, you'll find that giving this field of Ev is the same as adding that Ev to the BRST differential. Okay. And maybe more interpretationally, so I mentioned that a twist of a non-supersymmetric field theory, it's sort of, or of a non-gravitational supersymmetric field theory, it describes data that sort of just depends on this transversely holomorphic foliation. So twists of a supergravity theory, they'll govern deformations of a transversely holomorphic foliation. Okay. Okay. So my collaborators and I studied the following theory, which we conjectured describes the minimal twist of 11-dimensional supergravity on flat space. So the BV fields look as follows. So you have a divergence-free holomorphic vector field on C5, and you have a co-closed holomorphic one form on C5. The BV pairing, it pairs together these two, and it pairs together these two. So you should think that this field mu, its components in Gauss number 0, it describes maybe certain components of the metric that survive the twist. And certain components of gamma, for instance, the components that look like a 1, 2 form, those are supposed to describe certain components of the C field. Okay. And the interaction takes the following form. So we have two kinds of terms. One maybe looks kind of annoying. You have this geometric series in nu here. And the other one is hopefully reminiscent of the Chern-Simons term in 11-dimensional supergravity. So I claim, though this maybe looks kind of cumbersome, it's not so bad. There's a certain transcendental field redefinition that you can perform under which this basically gets related to something that looks a lot like the Kodaira-Spencer interaction. So without this term, you could think that the phase space of this theory, it describes the cotangent bundle to the moduli of Calabi-Yau structures on C5. And then this sort of deforms that cotangent bundle in some funny way. Okay. So we amassed quite a lot of evidence for this conjecture. In fact, I'd say it's basically a theorem. So let me describe some strands. So the weakest such check that you can perform, which is basically just a check of the underlying field content, you can compute a character of the space of local operators, where I mean things of non-zero ghost number, and you find something that agrees exactly with the graviton contribution to the M-theory index that was computed by Makrosov and others. Okay. A slightly more stringent check of the field contents, you can compute the minimal twist of the 11-dimensional supergravity multiplet directly using pure spinor superfield techniques, and you find something that matches exactly with the free limit of the theory on the previous slide. There was also a non-minimal twist of 11-dimensional supergravity that was studied by Costello and later by Eager and Honor that's defined on products of G2 manifolds and hyperkähler surfaces. And the theory that I described on the previous slide, it admits a deformation to this non-minimal twist. And moreover, Costello and Lee have conjectural descriptions of twists of type 2a and type 1 supergravity as closed string field theories associated to topological strings in 5 complex dimensions. And you can compute dimensional reductions of the model that I wrote down, and it recovers those sorts of conjectural descriptions. Okay. Then lastly, and sort of most stringently, you can sort of use these sorts of pure spinor superfield techniques that I mentioned earlier to twist the interacting theory, and you get the interaction that I wrote down in the previous slide. Okay. Now, perhaps the most surprising feature of this theory is that it's closely related to some of these infinite dimensional exceptional simple super Lie algebras. Okay. So it's a general fact about theories in the BV formalism that if you shift the fields and then look at the linearized BRST cohomology, you'll find something like a Lie algebra, what's called an L infinity algebra. So you should think that this describes the gauge symmetries that preserve the trivial field configuration. And if you do that on for the given theory, you find a certain extension of E510 by a 3 cocycle. So it's a Lie2 algebra. Okay. And I'll describe E510, and it'll be apparent that it's maybe describing something like gauge symmetries in a holomorphic version of 11-dimensional supergravity. So what is E510? It's the following super Lie algebra. So in even degrees, you have divergence-free vector fields on C5. In odd degrees, you have closed 2 forms on C5. and there's an odd bracket, you wedge together two closed two forms and then contract with the inverse of the holomorphic volume form, and that's divergence free because these are closed. Okay. And then the cocycle determining this extension, you wedge together two vector fields, contract with a two form, and then take the constant term. Okay.
The last thing.
The last line. I'm just this is a function. I'm just evaluating that function at 0 on C5. So I'm taking the constant term of that function.
This is what you do by the lead to extension.
Yeah. So a lead. Yeah. A 3 cocycle gives you a 3-ary bracket and defines a Lie 2 algebra.
Is it in any sense similar to this loop algebra kind of extension of Lie algebra?
This is a little different than the loop algebra type of extensions. So where this sort of comes from, so the C field, it's not exactly a 3 form. It's like a 3 connection on a 2 gerb. So its gauge transformations are really like a 3 group. And after the twist infinitesimally, that Lie 3 algebra becomes a Lie 2 algebra. So it's sort of coming from the fact that there's really like a tower of gauge transformations for the C field. It's a little bit different from these loop algebra type central extensions. It is true that in higher dimensions, though, those loop algebra type central extensions become these kinds of like L infinity extensions rather than the algebra type extensions. Yeah, thanks. Okay. So what can you do with this? So I mentioned this fact about the character of local operators. So local operators, again, I mean of non-zero ghost number, they're simply given by the Lie algebra cochains on this Lie 2 algebra. And there's an SU5 action on this thing coming from the SU5 action on C5. And you can compute a character and you exactly find the formula that you find in these papers of Nekrasov and Nekrasov-Vakunkov about the graviton contribution to the M-theory index. And this has a specialization that recovers things like the topological vertex. Okay. So let me now turn my attention to geometries that are sourced by M2 and M5 brains. So it turns out that such geometries will have asymptotic symmetries by 2 of the remaining 4 infinite dimensional exceptional simple super Lie algebras. Okay. So the first question we should ask is what the leading order coupling to M2s and M5s look like in the twist. And I mentioned that dimensional reductions of our model, they are equivalent to twists of supergravity and 10D that have descriptions in terms of closed string field theories of topological strings. And there's an open closed map which determines the form of the coupling to D brains. So we can make ansatz for what the coupling at leading order look like by asking that they sort of dimensionally reduce to what the closed open map tells you for the coupling to D2 and D4 brains. Okay. Then once we have those couplings, you do the same thing that you do in the physical theory, except in the twist, things like the there's sort of nothing akin to taking like the near horizon limit, I guess, because that direction becomes topological. Okay. So we have these couplings, the corresponding source equations look like this. And it turns out that you can just solve the linearized equations, and for type reasons, there'll be solutions to the full nonlinear equations. And then we just expand around these solutions, okay, after deleting the branes. Okay. In doing so, we get these conjectural descriptions for what the minimal twist of 11-dimensional supergravity on ADS4 cross S7 and ADS7 cross S4 looks like. This is a conjecture because rather than twisting the physical theory on these things, we've sort of back reacted in the twist, and it's not immediately obvious that those agree, but I'll present some checks of this conjecture momentarily. And here it's convenient to write flat space as the total space of certain vector bundles over the locus that the brane lives. That's not too important. In a moment, I'll do some counts, and this is just going to affect the powers of some fugacities that appear in the counts, just to match with things in the literature.
If you're saying it's not obvious that if you twist and then deform, it's not the same. It's not quite the same as introducing the two branes and then twisting it.
Absolutely. Yeah, I think in general, it's probably not true that backreacting commutes with twisting. For instance, the twist that you perform, certain branes might not survive the twist that you perform, but you could often add those branes back in by hand at the level of the twist or something. And
yeah, also, I guess it's also not obvious to me, also from the fact that in the physical theory, you would have had to take the near horizon geometry. ADS4 times S7, you can't really think of as a deformation of the flat space 11D theory in the untwisted case, right? You have to consider these M2 or M4, M2 or M5 rates, and then take this near horizon limit, only then you get the full enhanced supergravity. So I'm basically saying that the near horizon limit, that process, you're somehow mimicking in the twist theory.
so I think
sort of comes out automatically.
in the twist, at least if you start on flat space, the direction normal to the branes is often topological, I guess. Like if you compactify on a sphere that's linking the branes, then you'll have some holomorphic topological theory that's topological in the direction that's like perpendicular to the branes. So I think that makes the near horizon limit kind of like uninteresting in the twist. I haven't checked that carefully. Okay. Okay. So we can again test this conjecture across a couple of different strands. So one, we can count supergravity states, so field configurations that are localized at points on the asymptotic boundary of ADS. This slide is a little technical. I'm just describing how to construct vector spaces whose elements are those kinds of field configurations, at least the single particle states. Okay. And upon doing that, we can compute characters of these things with respect to an SL4 times SL2 that's acting in the ADS4 times S7 case, and then SL3 times SL2 times GL1 that's acting in the ADS7 times S4 case. And we get these answers here, and they agree exactly with single particle indices that enumerate gravitons on ADS4 times S7 and ADS7 times S4 respectively. Okay. That's maybe a first check. And so the second of these, it has a specialization that's induced by, in a sense that I'll describe, induced from the superconformal deformation that appeared at the beginning of the talk, that recovers this rational function here, the plothistic exponential, which is the Mach-Mahon function. So that suggests that the symmetric algebra of this thing wants to be sort of the vacuum module for some enhancements of, say, the W1 plus infinity algebra to 3 complex dimensions. Okay. So another check that you can do is you can try and match the symmetries. So in the physical theory, 11-dimensional supergravity on the ADS4 times S7 and ADS7 times S4 backgrounds, they have actions by the relevant superconformal algebras, which are different real forms of the same complex simple Lie superalgebra, OSP 8/4. And the commutant of the supercharge that you use to twist inside OSP 8/4 is isomorphic to OSP 6/2. So accordingly, you would expect that OSP 6/2 acts on the twisted versions of these backgrounds, and it does. So I mentioned that if you look at the parity shifts of the space of fields of a PV theory, and you look at the linearized cohomology, that's a Lie algebra, and there are Lie maps like this. Okay. Okay. Now, I mentioned that there's a close relationship with these backgrounds with 2 more of these exceptional gadgets. And this sort of comes from a way of recasting the decomposition of the KK spectrum into superconformal multiplets in terms of the twist. So of course, this is like a very classical result, maybe going back to people like Ganadin and Warner in the 80s. And there's a way of recovering this decomposition from the twist that reveals a hidden piece of structure. So each superconformal multiplet that appears, it's an irreducible module for another infinite dimensional exceptional simple super Lie algebra. Okay. So how does this work? So the theories on these backgrounds, they have certain C star actions which combine rescaling normal to the asymptotic boundary of ADS with a certain global symmetry. And the C star actions, they induce certain weight decompositions of these spaces of supergravity states that I was describing earlier. Okay. Of field configurations at the asymptotic boundary of ADS7 and ADS4. Okay. And this decomposition has the feature that if you look at the 0th weight space, that necessarily has to be some kind of Lie algebra because the C star action was preserving some Lie structure. And all the other non-zero weight spaces, they need to be acted on by that Lie algebra for the same reason. Okay. So what are the Lie algebras that you find in the 0th weight space? Well, they have the feature that if you look at Taylor expansion near the origin, so infinity jets at the origin and R times C and C3 respectively, you find these Lie superalgebras E16 and E36 that I was describing previously. And moreover, E16 and E36, they contain copies of OSP 6/2 as finite dimensional subalgebras. Okay, so this is really, in the sense, this is analogous to the appearance of vector fields on C in 2D chiral CFT. So let me maybe give some sense of what some of these Lie algebras look like. So E36, in even degrees, it looks like formal vector fields in 3 variables, semi-direct SL2 currents in 3 variables. In odd degrees, I have 2 copies of 1 forms twisted by k to the minus a half. The even part acts on the odd part in the obvious way. This acts by Lie derivative, appropriately twisted by divergences, and SL2 currents just act by the fundamental representation. And now there's a very non-obvious odd bracket that takes 2 elements here to an element here. So the first line lands back in the first summand here, and it uses a symplectic form on C2. And the second line lands back in this summand here, and it uses the projection from the tensor square of the fundamental to the adjoint. Okay. And again, all the other pieces of this weight decomposition, they are acted on by these Lie algebras. And these are precisely the superconformal multiplets that appear in the KK spectrum. Okay. So what do some of these modules look like? So the lowest pieces are closely related to the minimal twists of these free SCFTs in dimensions 3 and 6 that appeared at the beginning of my talk. So the lowest piece of the decomposition on ADS4 times S7, it looks like this. And likewise for ADS7 times S4. And if you look at compactly supported sections at the origin of these, those are the spaces of linear local operators for the minimal twists of the theory on a single M2 or M5 ring probing flat space. Okay. So it's sort of non-obvious that E16 acts on this thing. So I mentioned that you should think that the appearance of these exceptional symmetries, it's sort of enhancing minimally twisted superconformal symmetry. And E16, it was enhancing the minimal twist of 3D n equals 8 superconformal symmetry. But of course, the level 1 rank 1 ABJM theory, at the level of the Lagrangian, only sort of n equals 6 superconformal symmetry is manifest. And the fact that it has n equals 8 superconformal symmetry is due to a non-perturbative effect involving monopole operators. And indeed, if you try and write down currents for the E16 action, which we did in some work with Nick Garner and Brian Williams, you find that those currents will involve monopole operators. But here, sort of from how this appears in the KK spectrum on supergravity, you sort of get for free that E16 has to act. Okay. And you can compute characters of each of the modules that appear in this decomposition, and you indeed find things that match with characters of the superconformal multiplets that appear in the KK spectrum, and the specialization induced by the superconformal deformation, the sum of the first n of these characters, it will recover the vacuum character of the Wn plus 2 algebra. Okay. So in the remainder of the talk, I'll focus on some work that's more in progress that aims to maybe apply this E36 symmetry to say some things about 16th BPS local operators in the 62 theories of type A n minus 1. And our approach will be through something called twisted holography. So at its heart, the twisted holography program, it involves codifying the matching between boundary values of gravitational fields and sources in the CFT by way of an algebraic operation called Koszul duality. So I won't say too much about this operation in the talk, but the essence is that via this matching, boundary values of gravitational fields, they should couple to CFT local operators in a gauge invariant way. And the Koszul dual is sort of the universal way to solve this, if you will. Okay. And this is the fact that that universality is expressed by saying that there should be a map like this here. So the shriek denotes this Koszul duality operation. Okay. So there's supposed to be a system of compatible maps from the Koszul dual of local operators in gravity at the location of the brain, equivalently operators on a transverse boundary condition that lives at the asymptotic boundary of ADS7 to observables for the theory on n brains. And the system of compatible maps is supposed to become an isomorphism in the large n limit. Okay. So what's the idea? You can sort of twist both sides and make sense of these kinds of algebras at the level of the twist. But you can do that in gauge theory examples. Both of these will have sort of independent definitions, but here only the left-hand side does. So the idea is that we can try and use this kind of map to define what the right-hand side should be by maybe characterizing its kernel and co-kernel appropriately. And then we can, after we have some suitable definition of this right-hand side, we can try and recover various BPS invariants of 5D n equals 2 theories by dimensionally reducing this gadget. Okay. So let me first consider the large N algebra at tree level. So tree level, the large N algebra takes the form of a twisted enveloping algebra. And so it's an enveloping algebra of some central extension. And you can compute the cocycle in terms of Witten diagrams that involve this flux, but those Witten diagrams sort of grow and wieldy pretty quickly. But the restrictions to the lowest pieces of this decomposition, they're much more manageable. And moreover, the answers that you get are kind of nice. So here's the conjecture. So after deforming by the superconformal element, the lowest pieces of this decomposition, as we saw earlier, they'll localize to a copy of C inside of C3. And what will they look like? So the lowest piece, which was the minimal twist of the abelian tensor multiplet, its observables, they'll deform to the Heisenberg vertex algebra. Whereas the piece that looks like E36, it'll deform to the Virasoro vertex algebra. Okay. So what remains is basically to match central charges. Okay. So one lesson that we learn is that the map that we get from causal duality, it's supposed to be equivariance for the action of this kind of higher Virasoro algebra, this higher dimensional version of the Virasoro algebra that's built from E36. Okay, so local operators in the 16 PPS local operators of the 62-0 theory, they should transform in representations of this infinite dimensional thing. Okay, so we can try and characterize the kernel and co-kernel of this kind of map as E36 modules. Okay, and the kernel and co-kernel of this kind of map, they have interpretations as other kinds of non-perturbative objects in gravity, at least such as illustrated in certain examples. So say we were studying a gauge theory example, like the half BPS sector of 40 n equals 4. In the kernel of this kind of map, it's exactly trace relations. And there's work that illustrates in that example that you should think of things like giant gravitons as describing syzygies between trace relations when you resolve them freely over the closed ring sector. So there's a recent paper or a paper from 23 by Ji-Hoon Lee that illustrates that in that example. So the kernel of this kind of map has something to do with giant gravitons. And the co-kernel of this kind of map, well, characterizing the co-kernel of this kind of map in gauge theory examples, that's basically what's done in these papers on cohomological approaches to characterizing black hole microstates. The co-kernel is exactly those gauge invariant local operators that are not of multigraviton form, again, in gauge theory examples. So in this M theory example, we don't have some a priori description of the right-hand side, and there's sort of no analog of trace relations. So it's sort of hard to see how to generalize these kinds of patterns, but we do have the constraint that they should be E36 modules, okay? So the idea is that fluctuations of giant gravitons in EDS 7 times S4, say, they should organize themselves into E36 modules. Okay.
What was the syzygy?
Syzygies. So those are like relations between relations. Yeah, and so on and so forth. Yeah. Okay. So maybe the last thing I'll say is the following conjecture, which describes how maybe to write down some E16 modules that should describe the fluctuations of sort of singly wrapped giant M2 branes in ADS 7 times S4. So there's some work by Imamura that identifies superconformal multiplets in the 16 PPS spectrum that should come from singly wrapped giant M2 branes. And there's some work of Zeitlin and some co-authors that does some approximation to the kind of thing Samir was talking about yesterday to find the sort of first term in the giant graviton expansion by from some one loop computation involving giant M2 branes in ADS 7 times S4. And the conjecture is that if we throw in those singly wrapped giant M2 branes by hand and do the same kind of construction that gave me these spaces of supergravity states, but after throwing these sorts of things in by hand, the results, it'll be an E16, E36 bimodule whose character will be exactly the contribution of those singly wrapped M2 branes to the superconformal index. Okay. Moreover, under the superconformal deformation, this should, the symmetric algebra of this sort of thing, it should recover a certain bimodule that was studied in work of Gallardo and Rapchak, a bimodule for the, yeah, in their work on omega deformed twisted M theory. Okay, let me stop there. Questions?
Speculation about the other super.
Yeah, yeah. So there's another least superalgebra called E38, which looks very similar to E36. The odd part is a little bit larger, and I really want this to be related to Hull's like 64,0 superconformal theory that may or may not exist. Yeah, or like Hull has been speculating that there's a 64,0 an interacting 64,0 theory that dimension reduces maybe to 5D n equals 2 supergravity or something like this. And yeah, yeah, yeah.
2,0.
It's a gravitational theory that is supposed to have an action of the 64,0 superconformal algebra OSP 8/8. And I don't think the interacting theory has been like written down. But like, yeah, Chris Hull has some papers about this, presenting some sort of consistency checks that such a thing might exist. And yeah. Yeah.
Yeah, it's still highly speculative, right? 64,0, I understand, it's not really.
Yeah, yeah. Yeah, Hull's written down like a multiplet. I don't know if an interacting theory has been proposed, or yeah, it's still highly speculative. But I believe so. And yeah, I think it has the feature that it dimensionally reduces to 5D n equals 2 supergravity, the multiplet. Yeah. Yeah, and then there's, yeah, and then the last of the 5 of these exceptional gadgets is one called E4/4, and I really have no idea where that might arise in physics. Yeah. Yeah.
There are more questions, let's time. This morning,
So we can turn this off.
Workshops are not coming. But I will keep